Hey guys, so in the last lecture we have seen few examples. So in today's lecture we will see how the vibration frequency is measured with the help of some devices. In real life, how we measure the vibration. And this is the last topic of this chapter. There is forced damped vibration. So in this chapter, this last topic, that is how in real life we measure the vibration. What are the devices which are used to measure the frequency? So besides measuring the amplitude, so amplitude, velocity and acceleration of the vibration, it is very much important to find the frequency of the vibration. So we know that we can also find amplitude, uh, then velocity and also acceleration. It is x dot and x double dot. We can find this all, but the most important thing is to find the frequency, natural frequency of the vibration. So most frequency measuring instruments of the mechanical type are based on the principle of resonance. They are based on the principle of resonance. So these are usually one of the two kinds as discussed, as uh, we will discuss two kinds of uh, vibration measuring device. So first, let's start with first. So it is a single reed frequency meter or Fullerton tachometer. So a single reed frequency meter, single reed frequency meter, or can be called as Fullerton tachometer. So this instrument consists of variable cantilever strip or reed of spring steel. So let me draw the diagram first so you will get understand very easily. So let's draw the diagram. So as as you can see, so first we'll draw, sorry, a calibrated scale. So this is a calibrated scale. So this here there are markings on this scale. So these are the suppose markings. So this is a calibrated scale. And now with this scale at this start, the portion is called head. So this portion is called head, and this is pointer, and this is pointer, and this scale is connected with the scale is connected with here, that is this scale is connected here with, let me call this as thumb nut. So we will call this as a thumb nut. So thumb nut, this thumb nut, and here a variable cantilever strip. Here there is a variable cantilever strip. So this is variable cantilever strip. So this is variable cantilever strip, and here there are various nuts. clamped. So this is basically construction. So here you can see the instruments consist of variable length cantilever strip. So this is a variable length cantilever strip or reed, or you can call it as a reed of the spring steel. So one end of the strip is clamped and its free length can be changed by screw mechanism. So this end can be changed by the screw mechanism. So this can be changed. The length can be changed with the help of this screw mechanism. So changing the length directly affects the natural frequency of the strip. So if we change this length, it will directly affect the natural frequency of the strip. So the clamp end of the strip. So the clamp end of the strip is then pressed firmly in contact with the vibrating body. So this thumb nut, this end is pressed with the vibrating body. So this is pressed with the vibrating body, and the screw mechanism is manipulated to change its free length, and this is manipulated to change this free length here. This is done till the free end shows large deflection. So till the free end shows a large deflection here, at this instant, the natural frequency of the cantilever is equal to the exciting frequency. Till the natural frequency of the cantilever, this is equal to the exciting frequency. So this is the whatever the exciting frequency is there, they should match both. So length of the reed is calibrated in terms of frequency. So this works basically on the principle of resonance. If we can match the frequency of the exciting frequency, then we can directly find the frequency of the system. So this is one method for measuring the natural frequency directly. Now the second B, so that is multi-reed instrument. This multi-reed instrument, or we can call it as Fraham Fraham's tachometer. Fraham's tachometer. So here, what is the diagram? So this instrument contains number of reeds. So there are so many reeds with white tips arranged in the box. So with a white tips arranged in the box with a dull interior. So each reed is in the form of a cantilever carrying small masses at their free ends. So if I let me draw a diagram to explain. So this is white strips, you can call it white strips here. There are so many strips. So this instrument, as you can see here, it consists of number of reeds. So there are so many reeds here with white tips arranged in the box with a dull interior. So the interior here is very much dull. So it is just black color interior, and it is very much dull. So each reed is in the form of a cantilever carrying small masses. So each reed is in the form of a cantilever carrying a small masses at their free ends, thus having a different natural frequency. So each have a different natural frequency. When the instrument is attached, so when the instrument is attached here, so this is the, as you can see the diagram. So this is the mass at the end of each reed. It is attached. So you can say this is the whole diagram. This is a cross sectional or right hand side view, you can call it right hand side view of this diagram. So at the end there's a mass, and this is the reed is attached. So when the instrument is attached, so whenever the instrument is attached to this vibrating to the vibrating body, the reed whose frequency is closest to the exciting frequency will exhibit maximum amplitude. So whichever reed is closest to the uh, frequency, it will have maximum amplitude. So while other reeds would hardly move, so the frequency of this reed would be then be the frequency of the vibrating body. So it works same on the principle of resonance, that both the frequency will match. So the frequency of the reed would then be considered as the frequency of vibrating body, and thus the swinging white tip. So the swinging white tip can easily be observed against a dark interior. So this is all dark. So this all background is dark, and these tips are white. So this will be observed, which is vibrating very much high. So, and if the reeds are calibrated, the frequency can easily be read. So his frequency can be easily be read. So this is a second type of instrument called multi-reed instruments, or Fram's tachometer. Now the third type of instrument, that is stroboscope. Stroboscope. So this is a non-contact frequency measurement. So the above two which we have seen, they were contact frequency measurement. So in this non-contact frequency measurement instrument, it consists of a light source which emit pulses intermittently. So this emits light source which emit light pulses intermittently, that is after a certain period. So the frequency at which the light pulses are produced can be altered. So this frequency can be altered, and read from the instrument. So we can alter the frequency and we can read. So the instrument uses the principle of persistence of the vision to measure the frequency in the rotating body. So to do so, a desired point of vibrating body is viewed with the stroboscope, and so uh, with through stroboscope, uh, a desired a desired point of the vibrating body is viewed to the stroboscope. The point where will appear stationary if and only if the frequency of the rotation and the frequency of pulsating light is the same. So the frequency of the rotation and the frequency of the pulsating light, if both are same, in that case only the uh, the point will appear stationary. So the stroboscope can measure the frequency above 15 hertz. So it can measure the frequency above 15 hertz only. So this is a uh, non-contact type vibrate frequency measuring device. So as this is the last topic of this chapter, so I will just list out and revise all the equations used in this chapter or derived in this chapter. So we'll start with the governing equation of force damped vibration. So it was mx double dot plus cx dot plus kx is equal to f0 sine omega t. And here we got the solution as x is equal to x sine omega t minus phi, and x0 is equal to f0 by k, and magnification factor m is equal to x by x0 is equal to 1 upon under root 1 minus r square whole square plus 2 zeta r whole square. Now here the value of phi is nothing but tan inverse 2 zeta r divided by 1 minus r square. So this 2 zeta r divided by 1 minus r square. So here the magnification factor is maximum when r, this is maximum if we after taking derivation we get that when r is equal to under root 1 minus 2 zeta 1 minus 2 zeta square So the maximum magnification factor will be 1 upon 2 zeta under root 1 minus zeta square. Now this was regarding the force damped vibration. Now the next topic we have seen is force transmitted to the base. So how much force is being transmitted? So it is damping force plus spring force. So that is F of t. So we found that F of t is nothing but F0 into m into under root 1 plus 2 zeta r whole square. So here, so from this equation we got transmissibility ratio, that is Ft by F0. If we bring this on the right hand side, left hand side, so we got that it is nothing but m into under root 1 plus 2 zeta r whole square. This is the transmissibility ratio Tr. Now then we saw rotating and reciprocating unbalance. So rotating and reciprocating unbalance. Rotating and reciprocating unbalance. So m, the equation was mx double dot plus cx dot plus kx is equal to m e omega square sine omega t. So here we got the same equation, that is mx upon me is equal to the magnification factor, that is m dash r square, that is magnification factor m dash r square. So we can also write this as equal to 1 upon 2 and 2 zeta under root 1 minus zeta square. So this is for rotating and reciprocating unbalance. Then we saw base excitation. Base excitation. In that we have seen the x by y. So this is amplitude transmissibility, that is omega, that is m, magnification factor m into under root 1 plus 2 zeta r whole square. So we got the same equation for force transmissibility, and so for the force transmissibility here, that is transmissibility ratio and amplitude transmissibility, the equations are both the same here. So and we also got, then we found relative amplitude. We found relative amplitude. So for that we have taken d is equal to x minus y, and d is equal to, we got y r square m. M is nothing but magnification factor. So these are all the equations which we have discussed in this chapter, and I hope you understood this all equations. So we will see the next chapter, that is critical or whirling speed of the shaft. Then it is the last chapter of this portion, that is vibration. So critical and whirling speed of the shaft. So we'll see this in the next lecture. So, and we have seen two chapters till now, that is free vibration and forced damped vibration. And in free vibration, free undamped vibration, we have seen various equations, like for SHM, simple harmonic motion, dampers, and springs, and we have seen Newton's law and various laws. So hope to see you in the next lecture, and thank you very much.